Deep in the quiet university town of Greifswald, Germany, sitting inside a massive concrete hall is a machine that looks less like a power plant and more like a twisted sculpture from a terrifying sci-fi movie. Its geometry is chaotic. It coils and writhes like a metal snake eating its own tail. To the uninitiated, it looks like a mistake. But this machine, the Wendelstein 7X, has quietly shaken the foundations of the global energy industry. While the rest of the world was looking left, Germany looked right. While superpowers poured billions into one specific idea, German engineers spent 19 years building something everyone else said was too complicated to work. And now, they've achieved the impossible. They haven't just tamed the fire of the stars, they've found a way to keep it burning. Today, we are looking at the cover of the cryostat, the shell of a machine that has broken the curse of nuclear fusion. This is the story of the Rebel Path, the stellarator, and the startup that believes it can put a star on the grid in 10 years. To understand why this machine is such a radical departure, we have to understand the ghost we've been chasing for 70 years, fusion. The sun doesn't burn like a fire. It doesn't split atoms like the nuclear reactors we have today, which leave behind radioactive waste for thousands of years. The sun fuses atoms. In its core, gravity is so crushing that hydrogen atoms are forced together, merging into helium. Every second, 600 million tons of matter are converted into pure energy. Since the 1930s, physicists have known that if we could do this on Earth, the game is over. We win. 1 kilogram of fusion fuel, extracted from plain water, produces as much energy as 10 million kilograms of coal. The waste is mostly helium, the harmless gas in birthday balloons. But there is a catch that has haunted scientists for generations. Fusion only happens at 100 million degrees Celsius. At that temperature, matter isn't solid, liquid, or gas. It becomes plasma, a superheated electrically charged soup. And plasma is wild. It wiggles, it screams, it tries to escape. If that 100 million degree plasma touches the wall of a reactor, two things happen. The wall vaporizes and the plasma instantly cools, killing the reaction. You cannot put a star in a metal box. So, in the 1950s, a physicist named Lyman Spitzer at Princeton came up with an idea. Don't touch it, trap it. Build a magnetic cage to suspend the plasma in a vacuum, floating in empty space. He called his invention the stellarator. He named the project Matterhorn. But by the 1960s, the world had abandoned his idea. Fusion scientists faced a fork in the road. They could build tokamaks, or they could build stellarators. Both use magnets to trap plasma in a donut shape. The tokamak, favored by the Soviet Union and later the US, was simpler. It was symmetrical. The math was easier. But it required an electric current to flow through the plasma itself to keep it trapped. The stellarator was different. It required no current in the plasma. Instead, the twist needed to contain the fire was built into the magnets themselves. But the shapes required were nightmares of three-dimensional geometry. In the days before supercomputers, they were impossible to design. So the world chose the tokamak. It became the standard, the safe bet. Almost everyone gave up on the twisted magnets. It was too risky, too expensive. But Germany didn't give up. In the early 1990s, while other nations refined their tokamaks, the Max Planck Institute in Germany doubled down. They began planning the Wendelstein 7X. It would become the most complex engineering project ever attempted in fusion. It took 19 years to build. It cost over 1.4 billion euros. It required 1.1 million assembly hours. The heart of the machine is a set of 50 superconducting magnets. Each one weighs tons, yet is twisted into a unique, non-symmetrical shape. They had to be positioned with the precision of a Swiss watch, accurate within a single millimeter.
These magnets are cooled to minus 270 degrees Celsius, colder than deep space. Yet, just a few centimeters away, the plasma burns at 20 million degrees. The coldest thing on Earth and the hottest thing on Earth, sitting cheek to cheek. Why go to this trouble? Why build the impossible machine? Because tokamaks have a fatal flaw. That electric current running through the plasma makes them unstable. They suffer from disruptions, violent crashes where the plasma collapses. It means tokamaks can only run in pulses, on, then off, on, then off. You cannot power a city with a flickering light bulb. The stellarator, with its twisted magnets, doesn't need that current. It is intrinsically stable. Once you turn it on, theoretically, it can run forever. On December 10, 2015, after years of delays and fixing leaks, they finally turned it on. The magnetic field matched the computer predictions perfectly. The beast was awake. But waking it up was just the start. They had to teach it to run. For the last few years, the team at Greifswald, supported by Eurofusion and international partners, has been pushing the machine to its limits. And recently, they hit a milestone that changes everything. We often hear about fusion records measured in seconds, but in this game, time isn't the only metric that matters. It's the triple product: density, temperature, and confinement time. The Wendelstein 7X recently achieved a high-performance plasma discharge lasting 43 seconds. That might sound short compared to the 8-minute low-power tests of the past, but in terms of energy, it is revolutionary. They match the performance of the massive Jet tokamak in England. But Jet is huge and uses far more power. The German machine matched it with a smaller, more efficient design. They proved that you don't need the massive size of a tokamak to get high performance. Even more impressive was how they did it. It was a global effort. Oak Ridge National Laboratory in Tennessee built a machine gun for the reactor, a pellet injector that fires frozen hydrogen bullets into the plasma at 3,000 kilometers per hour. These pellets, frozen to just above absolute zero, refueled the fire without cooling it down. For the first time, AI-controlled systems adjusted the firing rate in real time, feeding the beast exactly what it needed moment by moment. This isn't just physics anymore. This is engineering. This is a power plant blueprint. And that is where the story pivots, from a government lab to a boardroom. While Wendelstein 7X was breaking records, a group of scientists inside the Max Planck Institute realized something. The machine they were working on was designed in the 1990s. Back then, supercomputers were 1,000,000 times weaker than the phone in your pocket. They realized that with modern AI and simulation tools, they could do better. They could take the proven stability of the stellarator and make it smaller, cheaper, and simpler. In 2023, Dr. Francesco Sciortino and his colleagues spun out of the institute to found Proxima Fusion. This is the first time a commercial company has spun out of the Max Planck Institute for plasma physics. Investors are lining up. Proxima raised 20 million euros in a seed round led by Red Alpine, with backing from the Bavarian government and the deep tech sector. Why the sudden cash flow? Because Proxima isn't just building a science experiment. They are building a product. Their design, unveiled in a peer-reviewed journal in 2025, is called Stellaris. The secret sauce? High-temperature superconductors.
Old superconductors need liquid helium and temperatures near absolute zero. New HTS magnets work at warmer cryogenic temperatures, minus 196 degrees Celsius, and can create vastly stronger magnetic fields. Stronger magnets mean you can squeeze the plasma tighter. Squeezing it tighter means you can shrink the reactor. Wendelstein 7X is a giant. Stellaris will be compact. Proxima plans to build a demonstration reactor called Alpha by 2031 and a full-scale power plant by the mid-2030s. That is 10 years away. For 70 years, the running joke has been that fusion is always 30 years away, but the timeline has collapsed. We aren't waiting on a physics miracle anymore. We are waiting on magnets and supply chains. If Proxima, or their competitors like Type 1 Energy in the US, succeed, the implications are staggering. Consider the fuel. Fusion runs on deuterium and tritium. Deuterium is found in seawater. Every single liter of ocean water contains enough deuterium to equal 300 liters of gasoline. The oceans alone could power human civilization for billions of years. Tritium is bred inside the reactor using lithium, the same metal in your laptop battery. We have enough lithium for millions of years. And unlike fossil fuels, the supply chain cannot be cut off by war or politics. You cannot embargo the ocean. Consider the safety. A fusion reactor cannot melt down. It is physically impossible. In a fission reactor, like Fukushima, the fuel stays hot for days after you turn it off. In a fusion reactor, there's only a few grams of fuel at any one time. If the power fails or the cooling stops or the magnets break, the plasma just touches the wall and goes out. It's like blowing out a candle. No chain reaction, no fallout. And consider the industry. We don't just need electricity, we need heat. Steel, cement, and chemical plants need 1,500-degree heat that solar panels and wind turbines simply cannot provide. Fusion produces that heat as a byproduct. It could decarbonize the heaviest industries on Earth. The path forward is crowded. There are massive tokamak projects like ITER in France and fierce competitors like Commonwealth Fusion Systems in Boston. But the stellarator has a unique advantage. It is the tortoise that caught up to the hare. It was the hard path, the path of complex geometry and twisted metal. But that complexity bought them stability. And in the energy grid, stability is everything. Dr. Thomas Klinger, the head of operations at Wendelstein 7X, put it best. The sheer fact that tokamaks look simpler to build is fading away. What happens next? Proxima is building a test magnet by 2027. The alpha reactor targets net energy by 2031. If they hit that target, the first commercial electrons from a stellarator could hit the grid in the late 2030s. Within the lifetime of most people watching this video, the era of burning dead dinosaurs could end. This twisted machine in a German town isn't just a sculpture anymore. It's a blueprint for the future. The sun is no longer just in the sky. It's in the bottle. And the bottle is finally ready to open. What do you think? Is the complexity of the stellarator the key to unlimited energy? Or will the simpler tokamak win the race? Let us know in the comments below. And to stay updated on the biggest engineering breakthroughs in history, make sure to like and subscribe.